Imagine you drill a perfect well that produces 10,000 barrels per day. What happens if your surface facilities can only process 6,000 barrels per day? The reservoir is no longer the bottleneck. Your surface facilities become the limiting factor. In fact, one of the biggest engineering challenges begins at the surface. The fluid arriving from the reservoir is not oil. It is not gas. It is a complex mixture of gas, crude oil, produced water, sand, wax, and sometimes corrosive gases such as hydrogen sulfide and carbon dioxide. None of these fluids can be sent directly to storage, pipelines, refineries, or export facilities. They must first be processed safely and efficiently. That is the role of surface facilities. In this chapter, we will study one of the most important pieces of production equipment, the separator. Although a separator may appear to be a simple pressure vessel, its design has a direct impact on production rate, hydrocarbon recovery, product quality, operating cost, and safety. Poor separation can cause compressor damage, pump failures, corrosion, hydrate formation, unstable production, and significant financial losses. By the end of this chapter, you will understand not only how separators work, but also how engineers select, design, and size them for real-field applications. Let's begin by looking at where separators fit within the entire surface production system. Before we study separators in detail, let's look at the bigger picture. Surface facilities are all the equipment installed after the wellhead to receive, process, measure, treat, store, and transport produced fluids. Their purpose is simple: convert a complex mixture coming from the reservoir into products that can be safely exported or sold. Think about what leaves the reservoir. It is rarely just crude oil. Instead, it is a mixture of natural gas, oil, produced water, sand, and sometimes impurities such as carbon dioxide and hydrogen sulfide. If this mixture were sent directly into a pipeline, refinery, or storage tank, it would create serious operational and safety problems. The first job of the surface facilities is therefore separation. We must divide the well stream into its individual phases. Once the fluids are separated, they must be processed using the appropriate equipment. Throughout this chapter, you will learn about the main types of separators and understand why different field conditions require different equipment. However, equipment alone is not enough. Every separator must be operated using control systems. Pressure controllers, level controllers, and safety valves ensure stable operation despite changes in production rate. Next, we will see that separators can be classified in several ways. They may be vertical or horizontal, two-phase or three-phase, and low-dash, intermediate-dash, or high-pressure. Each configuration has advantages and limitations. Selecting the correct separator is only part of the engineering task. We must also design and size the vessel so it provides sufficient residence time for effective separation while remaining economical. Finally, we will develop an engineering selection procedure. Rather than memorizing which separator to use, you will learn how engineers evaluate operating conditions, fluid properties, production rates, and facility constraints to make the best technical decision. By the end of this chapter, you should understand not only how separators work, but also how experienced production engineers select and design them for real-field applications. Before we begin, let's understand what you should be able to do by the end of this chapter. The first objective is to understand the fundamental principle of phase separation. When fluids leave the reservoir, they are no longer a single fluid. They become a multiphase mixture of gas, oil, and often water. Your first task as a production engineer is to understand how these phases naturally separate and how engineering improves that process. The second objective is to recognize the different types of separation equipment. In industry, you will encounter separators, scrubbers, knockout drums, flash vessels, expansion vessels, and mist extractors. Although they all remove fluids from one another, each serves a different purpose. Selecting the wrong equipment can reduce efficiency, increase operating costs, and even create safety risks. The third objective is to learn how separators are selected and sized. This is where engineering judgment becomes important. The choice between a horizontal or vertical separator is not arbitrary. It depends on flow rate, pressure, gas-oil ratio, water production, available space, and many other operating conditions. Once the type is selected, the vessel must be sized to provide enough residence time for effective separation. By the end of this chapter, you should be able to answer practical engineering questions such as: why was this separator selected? Will it handle future production? Is it correctly sized? How can its performance be improved? These are the same questions that production engineers answer every day in the field. So, this chapter is not just about learning equipment. It is about learning the engineering decisions behind reliable and efficient hydrocarbon production. Now that we understand the objectives of this chapter, let's see what actually happens after the fluids leave the well. Many people think production ends at the wellhead. In reality, the wellhead is only the beginning. The produced fluids must pass through a sequence of surface processes before they become marketable products. The first step is receiving the well stream. Fluids travel from the reservoir through the well and flow line into the production facility. At this point, the stream is a complex mixture of gas, oil, water, and sometimes sand or other impurities. The next and perhaps most important step is separation. This is the focus of this chapter. We separate the gas, oil, and water as early as possible. Early separation protects downstream equipment, improves operational efficiency, and allows each fluid to be handled independently. After separation, we move to measurement and control. We need accurate measurements of production rates, pressure, temperature, and liquid levels. These measurements are not only important for production optimization but also for reservoir management, production allocation, and regulatory reporting. The fluids are then processed and conditioned. Gas may require dehydration or compression before entering a pipeline. Oil may need stabilization to remove light hydrocarbons. Produced water must be treated to meet environmental discharge or reinjection requirements. Finally, the treated products are exported. Oil is sent to storage tanks or pipelines, gas enters transmission systems, and treated water is either disposed of safely or reinjected into the reservoir. Notice the three main fluid phases shown at the bottom of the slide. Gas, oil, and water each follow different processing paths because each has different specifications before it can be sold or reused. As production engineers, our job is to design facilities that maximize hydrocarbon recovery while maintaining safe, reliable, and environmentally responsible operations. Everything we study in this chapter supports four engineering objectives: improve separation efficiency, maximize hydrocarbon recovery, ensure safe and reliable operation, protect downstream equipment and the environment. Those objectives guide every engineering decision, from selecting a separator to determining its size and operating pressure. Now that we understand the role of surface facilities within the production system, let's examine the first and most important process in detail: how gas, oil, and water are actually separated inside a separator. Before we focus on separators, let's understand the complete journey of crude oil after it reaches the surface. Many people think oil flows directly from the well into a storage tank. In reality, crude oil passes through several processing steps before it becomes a saleable product. The process begins when the well stream arrives at the production facility. This stream is a mixture of natural gas, crude oil, produced water, and sometimes sand and other contaminants. The first and most important operation is primary separation. Here, the gas, oil, and water are separated into individual phases. This is the foundation of the entire surface processing system because every downstream process depends on effective separation. Once separated, each fluid follows its own processing path. The gas is typically compressed, dehydrated, and treated to remove impurities before being exported through a gas pipeline or used as fuel within the facility. The oil may still contain dissolved gas and small amounts of water. It therefore undergoes additional treatment, such as stabilization and dehydration, to meet export specifications before being sent to storage tanks or pipelines. The produced water contains residual oil and other contaminants. Before it can be discharged or re-injected into the reservoir, it must be treated to satisfy environmental and operational requirements. Notice that separation is only the first step in crude oil processing. Every subsequent operation, whether gas treatment, oil stabilization, or water treatment, depends on how well the separator performs. A poorly performing separator creates problems throughout the facility. Gas carried into the oil system can cause unstable storage tanks and pumping problems. Water carried into the oil stream reduces crude quality and increases transportation costs. Oil carried into the produced water system creates environmental compliance issues. This is why production engineers often say, the separator is the heart of the surface production facility. If the separator performs well, the rest of the facility operates efficiently. If it performs poorly, every downstream unit suffers. As engineers, our objective is not simply to produce hydrocarbons. Our objective is to deliver clean gas, stable crude oil, and treated water that meet technical, commercial, and environmental specifications. Now that we've seen the overall crude oil processing sequence, let's examine the most critical piece of equipment in that process, the production separator, and how it separates gas, oil, and water. Now let's connect all the equipment together and follow the path of the fluids through a typical production facility. Think of this as the roadmap of surface production. The process starts at the wellhead. The produced fluid, often called the well stream, enters the facility through the flow line. At this point, it is a multiphase mixture containing gas, oil, water, and sometimes solids. The first destination is the production separator. This is the most important piece of equipment because it divides the incoming stream into 3 individual products: gas, oil, and water. Let's follow each stream separately. The gas leaves the top of the separator. It may still contain small liquid droplets and water vapor, so it is normally sent to scrubbers, compressors, dehydration units, or gas treatment systems before entering the sales gas pipeline. The oil exits from the middle section of the separator. Depending on product specifications, it may pass through additional separation stages, heater treaters, or stabilizers before reaching storage tanks and export pipelines. The produced water leaves through the bottom of the separator. It is treated to remove residual oil and suspended solids before being re-injected into the reservoir or discharged according to environmental regulations. Notice that although the 3 streams follow different paths, they all depend on the performance of the first separator. If excessive gas remains in the oil, downstream pumps may experience cavitation. If excessive water remains in the oil, the crude may fail export specifications. If excessive oil enters the water treatment system, treatment costs increase and environmental compliance becomes more difficult. This illustrates an important engineering principle. The quality of the first separation determines the performance of the entire production facility. As production engineers, we do not optimize equipment individually. We optimize the entire production system. Every piece of equipment, from the separator to the export pipeline, is connected. That is why understanding the complete process flow is essential before designing or selecting any individual component. We've now seen where the separator fits within the production process. The next question is, what does a separator actually look like inside? Let's open the vessel and examine its major components and internal sections to understand how each contributes to efficient phase separation. Now that we understand the role of the separator within the production system, let's look inside the vessel. Although a separator may appear to be just a pressure vessel, it is carefully engineered to maximize separation efficiency. Every internal component has a specific purpose. A typical separator consists of 4 main internal sections. The first is the inlet or primary separation section. This is where the high-velocity well stream enters the vessel. An inlet diverter or deflector plate immediately changes the direction of flow. This sudden reduction in momentum causes the largest liquid droplets to separate from the gas almost instantly. In many cases, nearly 70 to 80% of the initial separation occurs in this first section. The fluid then enters the gravity settling section. Here, the flow velocity becomes much lower, allowing gravity to take over. Gas naturally rises toward the top of the vessel, while liquid settles downward. This section provides the residence time needed for efficient separation. The third section is the mist extractor. Even after gravity separation, the gas still contains very small liquid droplets. The mist extractor, usually made of wire mesh or vane packs, captures these droplets by causing them to collide, combine into larger droplets, and fall back into the liquid section. Its purpose is to ensure that only clean, dry gas leaves the separator. Finally, we have the liquid accumulation section. This is where the separated oil and water in a 3-phase separator are temporarily stored before leaving the vessel. This section also provides surge capacity, allowing the separator to handle short-term fluctuations in production without upsetting the process. Together, these 4 sections perform a sequence of operations. First, remove the large droplets. Second, allow gravity to separate the remaining phases. Third, polish the gas by removing fine mist. Finally, collect the separated liquids for controlled discharge. Notice that separation is not achieved in a single step. It is a combination of momentum change, gravity settling, droplet coalescence, and controlled liquid storage. This staged approach is what makes modern production separators both efficient and reliable. Of course, even the best designed separator cannot operate properly without automatic control. The pressure and liquid levels inside the vessel must remain stable despite continuous changes in production. In the next section, we'll examine the control devices that make this possible. We've now seen the internal sections of a separator. However, even a perfectly designed separator will fail if it cannot maintain stable operating conditions. That is the purpose of control devices. A separator is a dynamic system. Production rates change, pressure fluctuates, and liquid volumes vary throughout the day. The control system continuously adjusts the separator to keep it operating safely and efficiently. There are three primary control devices found on almost every production separator. The first is the pressure controller. Its job is to maintain a constant operating pressure inside the vessel. It does this by adjusting the gas outlet control valve. If the pressure becomes too high, the valve opens to release more gas. If the pressure falls below the desired value, the valve partially closes to retain pressure. Maintaining the correct pressure is essential because pressure directly affects gas density, liquid flashing, and separation efficiency. The second device is the liquid level controller. As oil enters the separator, the liquid level rises. The level controller continuously monitors this level and adjusts the liquid outlet valve accordingly. If the liquid level becomes too high, gas may escape through the liquid outlet. If it becomes too low, gas can bypass the separation process, reducing efficiency. Maintaining the correct liquid level ensures sufficient residence time for effective separation. In a three-phase separator, an additional controller monitors the oil-water interface. This allows the separator to discharge oil and water independently while preventing cross-contamination between the two phases. Finally, every separator is equipped with pressure relief devices. These are safety systems rather than process controls. If the vessel pressure exceeds its design limit, the pressure safety valve opens automatically to protect the separator from overpressure. This is one of the most important safety features in any pressure vessel. Notice that the separator itself does not make decisions. The control devices continuously monitor pressure and liquid levels and automatically adjust the outlet valves to keep the separator operating at its optimum conditions. Without these control systems, even the best designed separator would become unstable and inefficient. So far, we have examined how a separator works and how it is controlled. The next question is, are all separators the same? The answer is no. Separators are available in several configurations depending on their shape, operating pressure, and the number of phases they separate. In the next section, we'll examine the main classifications of production separators. Now that we understand how a separator works and how it is controlled, let's look at the different types of separators used in the petroleum industry. One of the most common questions asked by young engineers is, which separator is the best? The answer is simple. There is no universally best separator. There is only the most appropriate separator for a given application. Separators can be classified in several ways. The first classification is based on orientation or shape. A separator may be vertical, horizontal, or spherical. Each configuration offers different advantages depending on the production conditions, available space, and fluid characteristics. The second classification is based on the number of phases being separated. A two-phase separator separates gas from liquid. A three-phase separator separates gas, oil, and water into three individual streams. The third classification is based on operating pressure. Depending on the production system, separators may operate under low dash, medium dash, or high pressure conditions. The selected operating pressure directly influences separation efficiency, vessel size, and downstream processing. Finally, separators can also be classified according to their application. For example, a production separator continuously processes fluids from producing wells. A test separator measures the production from an individual well. A scrubber removes small liquid droplets from gas streams before compression. A flash separator operates at lower pressure to recover additional gas from crude oil. Each type is designed for a specific engineering purpose. The important point is that separator selection is not based on preference. It is based on production rate, gas-oil ratio, water cut, available space, operating pressure, economics, and the requirements of the downstream processing facilities. As engineers, we begin by understanding the operating conditions, then choose the separator that best satisfies those conditions. Over the next few slides, We'll examine the three most common separator configurations individually, beginning with the vertical separator, its construction, advantages, limitations, and typical field applications. Let's begin with the first and one of the most widely used separator configurations, the vertical separator. As its name suggests, a vertical separator is installed in an upright position. The well stream enters through the side of the vessel, where an inlet diverter reduces the fluid momentum and initiates the separation process. From there, gravity takes over. The gas, being the lightest phase, rises to the top of the vessel and passes through the mist extractor before leaving through the gas outlet. The liquid, consisting of oil or oil and water, falls to the bottom of the vessel, where it accumulates before being discharged through the liquid outlet under level control. One of the biggest advantages of a vertical separator is its ability to handle large volumes of gas. Because the gas flows upward over a relatively long distance, there is more opportunity for liquid droplets to settle out before the gas exits the vessel. Vertical separators are also very effective when sand or solid particles are produced. Gravity naturally causes these solids to settle at the bottom, where they can be removed more easily during maintenance. Another advantage is their relatively small footprint. When ground space is limited, such as in crowded onshore facilities, a vertical separator is often a practical choice. However, every design has limitations. Because the liquid storage section is relatively small, vertical separators are less suitable for high liquid production rates. They also provide a shorter liquid residence time than horizontal separators, making them less effective for separating oil and water when significant water production is present. For these reasons, vertical separators are commonly selected for high gas-oil ratio wells, gas condensate production, wells producing sand, applications where installation space is limited. Notice that we are not saying vertical separators are better than horizontal separators. Each design is optimized for different operating conditions. Engineering is about selecting the right equipment for the job, not finding a one-size-fits-all solution. If vertical separators perform well in gas-dominated production, what happens when a field produces large volumes of liquid or requires longer residence time for oil-water separation? For those conditions, engineers often choose a horizontal separator, which we'll examine next. Now let's look at the horizontal separator, which is the most commonly used separator in many oil production facilities. Unlike a vertical separator, the vessel is installed horizontally. This simple change in orientation creates a much larger liquid surface area and significantly increases the residence time of the liquid. Why is that important? Because oil and water need time to separate. The longer the liquid remains inside the vessel, the more opportunity gravity has to separate the two phases. This makes horizontal separators particularly effective for wells producing large volumes of liquid or with high water cut. Horizontal separators are available in two main configurations. The first is the single barrel separator. In this design, both gas and liquid separation occur within a single pressure vessel. It has a simple construction, lower capital cost, and is suitable for many standard production applications. The second is the double barrel separator. Here, an additional lower vessel is attached beneath the main separator. The upper barrel performs the primary gas-liquid separation, while the lower barrel provides additional liquid storage and improved oil-water separation. The extra liquid capacity allows better control of liquid levels and longer retention times, making double-barrel separators particularly suitable for high liquid production and three-phase separation. Like every design, horizontal separators have both strengths and weaknesses. Their major advantages include excellent liquid handling capacity, longer liquid retention time, improved oil-water separation, stable operation under fluctuating production rates. However, they also have some limitations. They require more installation space than vertical separators and are generally less effective when large amounts of sand are produced because solids tend to spread along the bottom of the vessel, making removal more difficult. So, when would you choose a horizontal separator? Typically, when the field produces significant amounts of oil and water, when high liquid throughput is expected, or when efficient three-phase separation is required. Notice the engineering trade-off. Vertical separators are generally preferred for gas-dominated production, while horizontal separators are usually selected for liquid-dominated production. The operating conditions determine the equipment, not the other way around. We've now examined the two separator types used most frequently in industry. There is one more configuration, although it is much less common today, the spherical separator. Let's see why it was developed and why its use has declined. We've looked at vertical and horizontal separators, which dominate modern production facilities. There is one more configuration worth discussing: the spherical separator. At first glance, it looks quite different. Instead of a cylindrical vessel, it uses a spherical pressure vessel to separate gas and liquid. So why would engineers choose a spherical shape? From a structural perspective, a sphere distributes internal pressure uniformly in all directions. This makes it very strong and allows the vessel to withstand high internal pressures with relatively uniform stress. It also occupies a relatively small footprint, which was attractive in older production facilities where space was limited. However, despite these advantages, spherical separators are rarely used in modern oil and gas production. The reason is simple. Their separation performance is limited compared with vertical and horizontal separators. Because the vessel is compact, there is less available volume for gravity separation and less residence time for the fluids. This reduces separation efficiency, particularly when production rates increase or when oil and water must be separated. Maintenance is another challenge. Installing and servicing internal components such as mist extractors and inlet devices is more difficult because of the vessel's shape. In addition, manufacturing a spherical pressure vessel is generally more expensive than fabricating a cylindrical vessel of similar capacity. Today, most operators prefer vertical or horizontal separators because they provide better separation efficiency, greater operating flexibility, easier maintenance, simpler expansion for future production. The spherical separator remains important from a historical and engineering perspective, but it is seldom selected for new production facilities. As engineers, understanding why a technology is no longer widely used is just as valuable as understanding why another technology has become the industry standard. We've now examined the three main separator configurations individually. The next step is to compare them side by side. We'll evaluate their strengths, limitations, and typical applications, and develop practical guidelines for selecting the most appropriate separator for a given production scenario. So far, we've classified separators based on their physical shape. Now let's classify them based on what they separate. This gives us two common configurations: two-phase separators and three-phase separators. A two-phase separator performs one task. It separates the well stream into gas and liquid. Notice that the liquid may still be a mixture of oil and water. The separator does not distinguish between them. They leave the vessel together through the liquid outlet and are separated later if required. Because of this simpler operation, two-phase separators have a simpler design, lower capital cost, fewer control systems, and lower maintenance requirements. They are commonly used in gas wells, gas condensate fields, and production systems where little or no produced water is expected. A three-phase separator, on the other hand, performs two separations simultaneously. First, it separates gas from the liquid. Then, because oil and water have different densities, it separates the liquid into oil and water. As a result, the vessel has three outlet streams: gas, oil, produced water. To achieve this, the separator includes an additional oil-water interface level controller, making the internal design and instrumentation more complex. Why go to this extra complexity? Because many mature oil fields produce significant amounts of water. Sending oil and water together downstream would increase treatment costs and reduce operational efficiency. Separating them at the earliest opportunity improves crude quality, reduces the load on downstream equipment, and simplifies produced water treatment. So, how do engineers choose between the two? The decision is driven by the produced fluids, not by personal preference. If the production stream contains mainly gas and liquid with negligible water, a two-phase separator is usually sufficient. If the well produces significant quantities of oil and water, a three-phase separator becomes the preferred option because it provides independent handling of all three fluids. Remember this simple rule: choose the simplest separator that meets the process requirements. Adding unnecessary complexity increases both capital cost and operating cost without improving production. Good engineering is about selecting equipment that is fit for purpose, not simply choosing the most sophisticated design. We've classified separators according to their shape and operating pressure. Now let's classify them according to the number of fluid phases they separate. This gives us two common configurations: two-phase separators and three-phase separators. A two-phase separator separates the well stream into gas and liquid. Notice that the liquid leaving the separator may still contain both oil and water. The separator treats them as a single liquid phase because further separation is either unnecessary or carried out in downstream equipment. This makes the vessel relatively simple. It requires fewer internal components, fewer control systems, and lower maintenance. As a result, two-phase separators have lower capital and operating costs. They are commonly used in gas wells, gas condensate fields, and production systems where very little water is produced. Now let's consider the three-phase separator. Here, the objective is different. Instead of producing only gas and liquid, we want three independent product streams: gas, oil, water. After the gas separates from the liquid, the oil and water remain inside the vessel long enough for gravity to separate them according to their densities. An interface-level controller continuously monitors the oil-water boundary to ensure that each liquid leaves through the correct outlet. This additional separation stage increases equipment complexity, but it provides major operational benefits. Oil leaving the separator contains much less water, improving crude quality and reducing downstream treatment. Likewise, the produced water contains less oil, making environmental treatment and disposal much easier. So, which separator should you choose? The answer depends entirely on the produced fluids. If water production is negligible, a two-phase separator is usually sufficient. If significant produced water is expected, a three-phase separator is almost always the better choice because it improves overall facility performance and reduces processing costs downstream. Remember this principle. Select the simplest separator that satisfies the process requirements. Adding unnecessary complexity increases both capital cost and maintenance without providing additional value. Good production engineers don't choose the most sophisticated equipment. They choose the equipment that best matches the operating conditions. Now that we understand the different separator configurations, the next question is, at what pressure should the separator operate, and where is each pressure range used? In the next section, we'll examine operating pressure classifications and their typical field applications. We've now seen that separators differ in their orientation and in the number of phases they separate. Another important classification is based on operating pressure. Why is operating pressure important? Because pressure determines how much gas remains dissolved in the oil and how much gas is released inside the separator. In general, separators are classified as high pressure, intermediate pressure, and low pressure separators. A high pressure separator is usually the first vessel after the wellhead. The produced fluid is still at a relatively high pressure, and only part of the dissolved gas is released. Keeping the pressure high at this stage minimizes sudden flashing, maintains stable flow, and reduces the size of downstream compression equipment. The partially degassed oil then flows to an intermediate pressure separator. Here, the pressure is reduced further, allowing additional gas to come out of solution. This recovered gas is valuable because it can be compressed and sold rather than remaining dissolved in the crude oil. Finally, the oil enters a low-pressure separator or stabilizer. At this stage, most of the remaining dissolved gas is removed, producing stable crude oil that satisfies storage and export specifications. Each pressure stage has a different engineering objective. High-pressure separators protect production and handle the initial well stream. Intermediate pressure separators maximize gas recovery. Low-pressure separators stabilize the crude oil before export. So, how do engineers decide which pressure to use? The answer depends on several factors: reservoir pressure, fluid properties, gas-oil ratio, export specifications, downstream processing facilities, economics. There is no universal operating pressure. The selected pressure must maximize hydrocarbon recovery while ensuring stable and efficient operation throughout the production system. So far, we've classified separators by shape, operating pressure, and the number of phases they separate. The next question is equally important. Should all the separation occur in a single vessel, or is it better to separate the fluids in multiple pressure stages? Let's examine one-stage, two-stage, three-stage, and four-stage separation systems. Until now, we've assumed that all separation occurs inside a single separator. But in many production facilities, that's not the case. Instead, the fluids pass through multiple separators operating at progressively lower pressures. This process is called multi-stage separation. Let's start with single-stage separation. Here, the well stream enters one separator, where the gas is removed and the oil is sent directly to storage or export. This arrangement is simple, inexpensive, and suitable for low production wells or facilities where product specifications are not particularly demanding. However, it is rarely the most efficient option. Now consider two-stage separation. The oil leaving the first separator is directed to a second separator operating at a lower pressure. As the pressure drops, additional dissolved gas is released and recovered. This extra gas has commercial value, and the remaining oil becomes more stable. Many production facilities use three-stage separation. After passing through the high-pressure and intermediate pressure separators, the oil enters a low-pressure separator or stabilizer. This final stage removes most of the remaining dissolved gas, producing crude oil that meets storage and pipeline specifications. In some large production facilities, particularly offshore platforms and central processing facilities, engineers may use four-stage separation. The additional stage allows even greater control of pressure reduction, maximizes hydrocarbon recovery, and improves product quality. However, it also increases equipment cost, operating complexity, and maintenance requirements. This raises an important engineering question. Why not use as many stages as possible? Because every additional separator adds capital cost, operating cost, instrumentation, maintenance, and space requirements. Beyond a certain point, the extra hydrocarbon recovered is worth less than the cost of installing another separator. This is where engineering economics becomes important. The objective is not to maximize the number of stages. The objective is to maximize the overall value of the production system. That is why many production facilities operate with 2 or 3 separation stages, providing an excellent balance between hydrocarbon recovery and economic performance. At this point, we understand how separators work and why different designs are used. But here's an important question. Why do 2 separators of the same size sometimes perform very differently? The answer lies in separation efficiency. Several factors determine how effectively a separator can separate gas, oil, and water. The first is operating pressure. Pressure controls how much gas remains dissolved in the oil. If the pressure is too high, insufficient gas is released. If it is too low, excessive flashing can create turbulence and reduce separation efficiency. The second factor is temperature. Higher temperatures reduce oil viscosity, allowing gas bubbles and water droplets to move more freely. This generally improves separation. However, excessive temperatures increase operating costs and may create other process challenges. Another important factor is fluid properties. Heavy oils with high viscosity separate much more slowly than light oils because the movement of droplets is restricted. Similarly, stable emulsions make oil-water separation significantly more difficult. The next factor is retention time. Gravity requires time to work. If fluids pass through the separator too quickly, gas bubbles cannot escape completely and water droplets cannot settle. Adequate residence time is therefore essential for efficient separation. Flow conditions also play a major role. Excessive inlet velocity or turbulence can remix the separated phases, reducing separator performance. This is why inlet devices and flow distributors are installed to calm the incoming fluid before gravity separation begins. Finally, separator maintenance is often overlooked. A damaged mist extractor, accumulated sand, fouled internals, or malfunctioning level controller can dramatically reduce separation efficiency, even if the separator was originally well designed. So, effective separation depends on much more than the size of the vessel. It depends on maintaining the right pressure, temperature, flow conditions, fluid residence time, and equipment condition. This highlights an important lesson. Good separator performance is achieved through both good design and good operation. A well-designed separator cannot compensate for poor operating practices, and excellent operators cannot overcome poor equipment design. Now that we understand the factors influencing separation efficiency, we can answer the next engineering question. What design requirements must a separator satisfy to consistently achieve efficient and reliable separation? In the next section, we'll examine the fundamental separator design requirements, including residence time, liquid capacity, gas capacity, and operational constraints. Now that we understand the factors affecting separation efficiency, the next question is, what makes a good separator design? A production separator is much more than a pressure vessel. It must be designed to provide efficient separation under all expected operating conditions. The first design requirement is adequate gas capacity. The separator must be large enough to reduce the gas velocity so that liquid droplets can fall back into the liquid section instead of being carried out with the gas. If the gas velocity is too high, valuable liquid hydrocarbons are lost, and downstream compressors may be damaged. The second requirement is adequate liquid capacity. The vessel must have sufficient volume to temporarily store the produced liquids while maintaining stable liquid levels. This allows the level control system to respond smoothly to changes in production without causing flooding or liquid carryover. The third and perhaps most important requirement is retention time, also called residence time. Retention time is simply the average time that the liquid remains inside the separator. Why is this so important? Because gravity needs time to separate the different phases. If the liquid leaves the separator too quickly, gas bubbles remain trapped in the oil, and water droplets do not have enough time to settle. The result is poor separation and lower product quality. On the other hand, making the separator excessively large is not the answer. Larger vessels increase capital cost, occupy more space, and add unnecessary weight, especially on offshore platforms. The engineer's challenge is therefore to provide sufficient retention time without oversizing the vessel. Finally, the separator must satisfy several practical requirements. It must operate safely over the expected pressure range. It must be easy to inspect and maintain. It must accommodate future production changes. And it must achieve all of this at the lowest practical cost. This illustrates an important engineering principle. The best separator is not the largest separator. It is the smallest separator that consistently delivers the required separation performance. That balance between technical performance and economic efficiency is the essence of good engineering design. Once the design requirements are established, the next step is to convert those requirements into actual vessel dimensions. In the next section, we'll develop a separator sizing methodology, including gas capacity calculations and liquid capacity calculations used in engineering design. Up to this point, we've discussed separator selection from a qualitative perspective. Now we move to engineering design. The question is no longer which separator should I use. The question becomes, how large should the separator be? Separator sizing is based on two independent design checks. The first is the gas capacity calculation. The objective is to ensure that the gas velocity inside the separator is low enough for liquid droplets to settle before reaching the gas outlet. If the gas velocity is too high, liquid droplets become entrained in the gas stream. This phenomenon is known as liquid carryover. It reduces product quality and can damage downstream compressors and gas processing equipment. Engineers typically estimate the allowable gas velocity using the Souders-Brown equation, which relates gas velocity to the density difference between the gas and liquid phases. The second design check is the liquid capacity calculation. This calculation ensures that the separator provides enough liquid volume to achieve the required retention time. Remember, gravity cannot separate oil and water instantly. The liquid must remain inside the vessel long enough for gas bubbles to rise and water droplets to settle. If the vessel is too small, the residence time becomes insufficient, resulting in poor separation and unstable operation. Once both calculations are completed, we compare the results. If the gas capacity calculation requires a larger vessel, then gas capacity controls the design. If the liquid capacity calculation requires a larger vessel, then liquid capacity controls the design. In practice, the final separator dimensions are always governed by the more restrictive requirement. This is a common principle in engineering design. You satisfy all design constraints, but the largest requirement determines the final equipment size. Notice that separator sizing is not based on guesswork or experience alone. It is based on fluid properties, production rates, operating pressure, temperature, retention time, and established engineering correlations. That is why two wells producing the same amount of oil may require completely different separator sizes if their gas-oil ratio, water cut, or operating conditions are different. Now we've reached the engineering calculations that determine the size of a separator. Until now, we've discussed the principles of separation. This slide answers a practical engineering question. How large should the separator be? A separator must satisfy two independent design criteria. The first is the gas capacity calculation. Its purpose is to ensure that the separator can handle the maximum expected gas flow without liquid droplets being carried out with the gas stream. To estimate this, engineers use the Souders-Brown equation, shown on the left. This equation calculates the maximum allowable gas velocity, which depends primarily on the density difference between the gas and liquid phases and an empirical constant, K, that reflects the separator design and service conditions. Notice the table beside the equation. For clean service, higher gas velocities are acceptable. However, for foaming fluids or difficult service, the allowable velocity must be reduced to prevent liquid carryover. This is why selecting the correct value of K is just as important as performing the calculation itself. The second design criterion is the liquid capacity calculation, shown in the middle of the slide. Here, the objective is different. Instead of controlling gas velocity, we determine whether the separator provides enough liquid volume to achieve the required retention time. The equation relates the liquid flow rate to the effective separator length, liquid loading rate, and separator geometry. Again, notice the recommended liquid loading values. A separator handling clean fluids can accommodate higher loading rates, whereas separators handling foaming fluids or solids require much lower loading rates to maintain good separation performance. On the right-hand side, you'll see the key design inputs. Before performing any sizing calculation, the engineer must know the production rates, operating pressure and temperature, fluid densities and viscosities, expected operating range, and any corrosive or difficult operating conditions. Finally, don't overlook the engineering notes at the bottom. Always use actual operating conditions, apply appropriate design factors, select conservative values of K and liquid loading, and verify the final design with pressure drop and level control checks. Remember this important principle. Gas capacity protects the gas outlet. Liquid capacity protects the liquid outlet. A well-designed separator must satisfy both requirements. The final vessel dimensions are therefore governed by the more restrictive of the two calculations, ensuring safe, efficient, and reliable operation throughout the life of the facility. We have now covered the complete engineering workflow, from understanding the production process to selecting and sizing separators. In our final slide, we'll bring everything together using a separator selection matrix and summarize the key engineering principles you should remember from this chapter. We've reached the end of this chapter. Let's step back and bring everything together. Throughout this lecture, we've learned that separator selection is not about choosing the most expensive or the most sophisticated equipment. It is about selecting the separator that best matches the production conditions. As production engineers, we should always ask a series of questions before selecting a separator. First, what fluids are being produced? If the well produces mainly gas with little water, a two-phase separator may be sufficient. If the production includes significant oil and water, a three-phase separator is usually the better choice. Second, what are the production rates? High gas rates often favor vertical separators. High liquid rates generally favor horizontal separators because they provide greater liquid retention time. Third, what is the operating pressure? High-pressure systems require separators capable of safely handling the wellhead conditions, while lower pressure stages maximize hydrocarbon recovery and produce stable crude oil. Fourth, what are the field constraints? Do we have enough space? Is the facility offshore, where weight and footprint are critical? Will production increase over time? These practical considerations often influence the final design as much as the process calculations. Finally, does the design satisfy both gas capacity and liquid capacity requirements? Remember, separator sizing is controlled by the most restrictive design criterion. Now let's summarize the key lessons from this chapter. First, a separator is not simply a pressure vessel. It is the first and most important processing unit in a production facility. Second, efficient separation depends on good engineering design, proper operating conditions, and reliable control systems. Third, there is no universal separator. The correct choice depends on fluid properties, production rates, operating pressure, water production, available space, and economics. Finally, good engineering is always a balance between technical performance, safety, reliability, and cost. That balance is what distinguishes engineering from simply following design equations. As you continue your studies, you'll discover that these same principles apply not only to separators but to every piece of production equipment. The goal is never to design the biggest system or the cheapest system. The goal is to design the right system. That is the essence of production engineering. Before we finish, let's review the most important lessons from today's lecture. If you remember only 5 points from this chapter, they should be these. First, the purpose of a separator is simple. Its job is to separate the well stream into individual phases so that gas, oil, and water can each be processed efficiently. It is the first and one of the most important units in every surface production facility. Second, separators rely primarily on gravity. They do not force the fluids apart. Instead, they provide the right conditions of pressure, flow velocity, and residence time so that nature can do the work. Third, there is no single separator that is best for every application. The choice between vertical, horizontal, two-phase, three-phase, and multi-stage separation depends on the production rate, fluid properties, gas-oil ratio, water cut, operating pressure, and field constraints. Fourth, good separator performance depends on both good design and good operation. A well-designed separator can perform poorly if the pressure, liquid level, or maintenance is not properly managed. Likewise, good operators cannot compensate for a poorly designed separator. Finally, engineering is about making informed decisions. When selecting a separator, we must consider technical performance, safety, reliability, operability, and economics together. The objective is not to build the largest separator or use the most complex design. The objective is to select the right separator for the specific operating conditions. I hope this chapter has shown you that separator selection is not simply a mechanical design problem. It is an engineering decision that directly influences production efficiency, hydrocarbon recovery, operating cost, and facility safety. As you progress in production engineering, you'll find that this decision-making approach applies to every piece of equipment you design or operate. Thank you, and I'm happy to answer any questions. The following nomographs are provided for information and historical context only. It represents a sizing approach commonly used in older separator design manuals. Modern separator sizing is typically performed using engineering equations, spreadsheets, process simulation software, and vendor-specific tools. Common methods include the Souders-Brown equation, Excel-based calculations, and commercial process simulators such as Aspen HYSYS, VMG, PetroSIM, and other specialized design software. While nomographs are useful for understanding the fundamentals and historical development of separator design, they are rarely used as the primary sizing method in current engineering practice. Modern workflows rely on more detailed calculations that consider fluid properties, operating conditions, separation efficiency, and design constraints.